Welcome to part C of the chapter 4 lecture video. In this video, we're going to do a quick just refresher of some of the things you might face with node voltage, and then we're going to jump right into mesh current. We went over in the past two videos, we were talking about node voltage. I just want to kind of clarify one of the challenges with node voltage is, most people can follow the steps, labeling the nodes, choosing an essential node, or choosing a reference node, labeling the essential nodes. And then the problem basically becomes, how do we write the Kirchhoff's current law to each node, no matter what kind of junk we have in these little branches between our essential nodes? And there's a few things that can show up in those branches between essential nodes that can throw you off. One of those being a voltage supply. So we talked last time a lot about if you have a voltage supply between two essential nodes and neither of them are the reference node, then you have to use the supernode technique is what we talked about. And that's, this version up here. That's a case where you do supernode. If in between two essential nodes, you see this show up in the middle, either supernode, or if one side, either A or B, is connected to your reference node, then you know the voltage, right? In this case, if B were our reference node, and we were looking for the current flowing out of A, we would just say, well, hold up, we know the voltage of A. If B is our reference node, then A is 10 volts, and we don't have to write the equation at node A. There's a few other things, though, a few other issues that can show up in between nodes. One of the biggest ones is something like this. If you have a voltage supply, but there's also resistors. If there's a voltage supply, but there's also resistors, then you're going to have to usually switch the order of these. So we said things in series, you can change their order, but not their orientation, without it impacting the overall equation for your system, right? So without impacting your overall system. So in this case, if we were given a resistor and a voltage supply and a resistor where it's not, we can't just immediately say, what's the voltage on this side of the resistor minus the voltage on this side divided by the resistance? That's normally how we do current. Normally we want to do current, we'd say, let's write the voltage here minus the voltage here divided by the resistance, and that's going to be the current flowing in that direction. Well, in this case, that's not quite so simple. But what we can do is we can reorder this to look like this, and now we can say, okay, what's the voltage on this side? That's VA. And what's the voltage on this side? That's VB plus 10, right? Because we have VB over here, and then we go up 10 volts for that supply. So now we can say the voltage on this side of this collection of resistors is VA, minus the voltage on this side, which is VB plus 10, divided by the total resistance. So we can write our expression like this when we encounter something like this. What about when we have current supplies? So when doing the node voltage technique, if we have a current supply, that's great. A current supply means, remember, we're writing the Kirchhoff's current law equation. So we're writing the collection of current. So if we see a current supply, our job's done. We know the current in that branch. We know, in this case, if we were writing the equations at node A and we were trying to find the current flowing between node A and node B in that direction, from node A to node B, flowing out of node A, then, and we have a current supply, that's it. We know we have negative 3 amps flowing from A towards B because we have 3 amps flowing from B towards A. What about if you have all this other junk? What if you have a current supply in series with a bunch of stuff? Well, when you have things in series with a current supply, they don't impact the rest of the circuit. You're still going to have, in this case, you're still going to have 2 amps flowing here no matter what. You could toss as much junk in here in series as you want, and you're still going to have the same current because that's what the current supply is doing. It's providing the same current. The only thing that's going to throw you off in this situation is if you have 2 current supplies in series, and again, that's the rule we talked about at the very beginning of the class. If you have multiple current supplies in series, they all have to have the same magnitude in the same direction, or your circuit is invalid. So if you encounter that where you have a current supply in series with a current supply, well, now you're either in a situation where we're trying to trick you by giving you an invalid circuit, or they're just the same magnitude in the same direction and you don't worry about it. So again, in this case, it doesn't matter what junk we had in here, the current flowing from A to B is going to be 2 amps. So, okay. So that's a lot of times what happens is students will encounter, they'll be doing a node voltage problem, everything's going fine, then they encounter something weird. It's usually a current or a voltage supply. And a lot of times what students have a tendency to do is they will accidentally treat a current supply as a voltage supply, or they'll accidentally treat a voltage supply as a current supply. Or they'll do some weird hybrid where they'll somehow, if there's just a voltage supply, they'll divide it by some resistance. I don't know where that resistance is coming from. They're just They just know they have to have voltage divided by resistance, so they do that. So be careful when doing node voltage to pay attention to these special cases that we just went over. Okay. So now we're going to talk about the mesh current technique. So the mesh current technique is the other version of our broad, big picture technique that we can use to solve any unknown circuits. And it is the complement of node voltage, meaning whereas node voltage, we run around two essential nodes and we wrote Kirchhoff's current law equations. Mesh current, we're going to go around these essential meshes and write the Kirchhoff's voltage law equation. So one of them, node voltage, we're solving for unknown voltages. Mesh current, we're solving for unknown currents. But other than that, they basically are the same kind of idea, which is we solve for a limited subset of variables. So we're not going to solve necessarily for every single current in our circuit. We're going to solve for just these essential currents. Solve for those and then use those minimum number essential elements of our circuit to find any other unknowns we're trying to find. So let's walk through the process of the mesh current technique. Luckily, it again has a process just like node voltage. So the first one is we identify, label meshes. So meshes, I sometimes call them essential meshes. Meshes just refer to, if you go back to our descriptions at the beginning of chapter 4, meshes refer to a closed path in a circuit that doesn't contain any other closed path. So a complete closed loop in a circuit that doesn't contain any other closed loop. So this is a mesh by the definition of meshes, and this is not. Why is that big one not? That big one isn't because it encompasses two submeshes. So basically, if you can take I'm mixing mesh and essential mesh here. I used to call it essential mesh. The book doesn't call it essential mesh anymore. If your closed path through a circuit contains more than one closed path within it, then that path is not a mesh, what the book calls a mesh, what I sometimes refer to as an essential mesh. So when we say we are picking essential meshes, that means we're picking these loops in our circuit that don't contain any subloops. So in that case, it would be these two loops here. And then what we're doing is, once we've identified those, and we'll label them IA and IB, and again, we're just picking labels, just picking variable labels. Now we're going to write the Kirchhoff's voltage law equation around each one of these meshes. So basically, we're going to go around this closed path, and each of them, and for each one of these closed paths, we're going to go around writing the sum of the voltage drops, and that should equal 0. And that'll give us an equation for each one of these essential meshes. Then the next step is we solve this system of equations to find our mesh currents. And once we know our mesh currents, we can find the current through any branch in our circuit by noting that branches shared by two meshes have currents equal to the combination of the two meshes. What does that mean? That means if we want to look at this current I3, so as labeled in this circuit, I3 is the current flowing down through this 10 ohm resistor. Well, if we look at this mesh IA is traveling down through the resistor, and IB, as labeled, is kind of traveling up through the resistor. So what's the total current flowing down through this resistor? This I3. In this case, I3 is going to equal IA, because IA is flowing in the same direction as I3, minus IB, because IB is flowing in the opposite direction of I3 as labeled. So what we're doing is, rather than solving for 1, 2, 3 unknown currents in this circuit, we're only solving for 2, but we're recognizing that we can find these other currents by taking a combination of these essential mesh currents. And this is kind of a little weird, because essential meshes, we're kind of thinking about current as if it's swirling around in these little loops in our circuit. We're thinking about current, like we have these little whirls, little swirly whirlies of current that are spinning around, and where they touch each other, it's like one vortex touching another. We have this combination of streams. And is that really the way it works? Do we actually have, in this wire here, do we actually have, half the wire is a current flowing this way and the other half is a current flowing this way? No. So we don't actually have these two currents that are swirling in opposite directions, but mathematically it works out the same. Why does mathematically it work out the same? So this is if we think about the current swirling, we have this I3 equals IA minus IB. Why does the math work out? Well, let's think about just this node. Let's think about just looking at this node and applying Kirchhoff's current law. If we were wondering, based on this node, how much current was flowing down here, what would that be? The current flowing out of this node would be the current flowing in minus the other current flowing out. Or another way to put it is, if we did a Kirchhoff's current equation at this node, and we did the sum of the currents flowing out, we could say negative I1 plus I3 plus I2 equals 0. Or rewriting that, we'd have I3 equals I1 minus I2. And it should be noted that I1 is IA. IA is the only current swirling here, and I2 is IB. IB is the only current flowing here. So this thinking about current as these little swirls that are spinning around inside of our circuits for the purposes of solving mesh currents works out okay because of Kirchhoff's current law. If we do a Kirchhoff's current law equation at the nodes where we have these junctions, we will find that yes, in fact, the current at that shared branch is equal to this combination of these kind of imaginary swirls of current. So it does work out mathematically. No, we don't actually have, it's not actually like a highway where we have some current flowing in one direction and some current flowing the other direction, and the total current is the amount. But mathematically, it works out the same if we sort of analyze these circuits as if they have these meshes of current. Okay, and then once we know these unknown currents, we can solve for our unknown circuit values. So, we can solve for, once we know all the currents in the circuit, power, voltage, whatever is fairly easy. The only thing that's challenging sometimes to solve for in a mesh current situation is sometimes the voltage across a current supply is tough to find. So sometimes the voltage across a current supply, the only way we can solve it is by just doing the whole Kirchhoff's voltage law and saying whatever voltage is left over, that's the voltage across our current supply. We had to do the same thing with node voltage if we ever wanted to find the current through a voltage supply. So if we ever wanted to find the current through a voltage supply, say we were doing, supernode or in the node voltage approach, the only way to find a current through a voltage supply sometimes was to, if there was no resistor in series with that voltage supply, the only way to find it was to do a Kirchhoff's current law analysis and just say whatever current's left over this node, that's the current through this supply. So that's the wiggle, that's the wrinkle in this approach. What's challenging that requires KVL or KCL in the case of mesh current is finding the voltage across current supplies. And what's challenging in node voltage is finding the current through voltage supplies. So as long as we kind of keep that in mind. And the biggest thing is just when you bump into this, when you're doing these problems, if you bump into a situation and you say, whoa, this is a little weird, this isn't what I was expecting, stop yourself and go back and look at these slides, look at these examples and think, okay, what do I do in this situation? When I have a current supply and the technique that I'm using is this, all right, what was I supposed to do to handle that situation? And if you stop yourself when you see those things pop up, when you say, okay, this isn't straightforward, something weird is happening, if you slow yourself down and really be deliberate and think about it, you'll tend to avoid making mistakes there. A lot of times what students do is just, they'll see a supply and they don't know what to do with it, and so they just pretend like it's a supply that they do know what to do with, and they take a current supply and divide by resistance in order to get a current, and that's not going to do it. Or they take a voltage supply and multiply by resistance in order to get a current, and that's not going to do it either. So just, it's, going through examples of this, recognizing it is the best thing you can do to get these correct. I also kind of want to take a little step back when we talk about this, and I'm going to do an example really quick before we forget about this process that I just talked about. But by now, a lot of you there's a good chance you finished the first midterm if you're taking this class. If you're just watching this video on YouTube and whatever. But if you just finished the first midterm, a lot of, typically in this class, the first midterm is a little squirrely in that there's a big spread of performance on it. And one of the things I said at the beginning of this class is the stuff we go over in this class is not intuitive. The things we go over in this class these are not things that should just make sense. These are not things that will automatically feel right. These are things that are confusing, they're non-intuitive, they're challenging, they require a process. And like I said at the beginning, a lot of times students who are very good, very smart, very high-performing students can struggle with these things. And a lot of times that struggle is this transition from intuiting your way through a problem to the struggle to developing a technique, adopting a technique, and applying a technique consistently in a way that you've practiced many times over so you know it's going to work correctly. If you're still at this point where you're struggling with node voltage or mesh current or some of these earlier concepts we talked about, don't let it go too far before you get those things firmed up. So the homework in this class is really important. Doing these examples is really important. a lot of times what happens is students will, it's easy when I'm doing it for you in a video to follow along and say, oh, okay, I guess that makes sense. I guess that makes sense. But really what you need to understand this stuff is do it yourself and then make a mistake. And when you make a mistake and you look at either a solution or you look at the solution that I did, stop yourself and say, why did that person do something different than what I did? And that's usually that stopping yourself and saying, wait, why did they do this the way they did it? That's typically, once you're able to answer that question in your mind, that's typically when everything kind of snaps together and makes sense. But to do so, you need to, as you're going through this stuff, to be deliberate about try it yourself. When you first see it, say, can I do this? And if you can't, that's fine. That's part of the process. But if you can't, when you see it be done, ask that question. Even if you're not talking to me live, if it's in office hours, it works great. But even if you're not talking to me live, be sure to ask that question of, wait, why did they do it that way? If you're doing node voltage, if you're doing voltage divider, a lot of times it's, wait, why did you use that voltage as the voltage in the voltage divider equation? And it's okay to be confused by that stuff because it's confusing. But really stopping yourself and saying, wait, why was this the voltage that was used? Or wait, why was this the REQ that was used in this equation? Because once you can kind of ask that question, recognize that's where the issue is, and then sort of recognize for yourself why that was the version that was used, that's really where you're going to start to get comfortable doing these successfully over and over and over again. So even though chapter 4 is kind of a breath of fresh air in the sense that it's a technique, if some of these old techniques and concepts are challenging to you, don't let it go too far. Don't let it go too long without correcting it. So if you bomb the first test, these things happen. And we've had lots of students bomb the first test. I've had a student who got a 30 on the first test who ended up getting an A in the class. Or maybe an A minus, I can't remember. But it was, but also one thing to note is we recognize that students will struggle with these concepts. And what we like to see is it's okay to struggle. It's okay to have a bad midterm early on. It's okay to not get something for a while early on. But really, you want to try to correct that and you want to master that. And if by the time you get to the final, these things that you were clearly not getting in the first exam are things that you've mastered, if they're things that you can just, boy, you got it now and you really understand it, that's our goal. Our goal is to make sure that you're able to really piece these things together, that you're able to really master the material. And if you had a rough exam early on, that's okay. It's okay. The big thing is to recognize it, correct it, and learn as you go forward. Because if anybody out there is feeling like, man, I bombed the first exam, this stuff isn't for me, I can't get this stuff, I'm not getting this stuff, you gotta recognize that that's a process that almost everybody goes through at some point in time. And some people went through that in physics, some people are going through it now, some people are better at hiding it even though they're still going through it now. But I can remember when I took this class, when I did this class a long time ago, I can remember doing homeworks and spending countless hours on homeworks because I would look at a problem and I would just say, why on earth did they do it this way? And I would struggle for forever on these problems. And for me, what motivated me was I had this fear, this incredible fear of getting to an exam or being asked how to do something and not knowing how to do it. I always hated that feeling of not knowing how to do something that I might be expected to know. And so that kind of motivated me. But without that, if I were taking this class alone from home, it would be even more difficult for me. So really trying to find a technique for you, trying to find a way that enables you to work through these problems in this way and to ask these types of questions and to get the answers that you need is going to be really important for your success. But everybody can do this stuff. If you're struggling with it, that's okay. Just lean into that struggle and be open about it, right? There's no dumb questions in the sense of, why on earth did you use that? I just go through it in this. I try not to make too many mistakes in these video series, but that's because I'm being deliberate about, trying not to make mistakes. In real life, I've made tons of mistakes, and there's concepts that are challenging for me to understand, and so it's totally expected that the same be the case with you. Just try to make sure you push through those misunderstandings, that you ask whatever question, no matter how dumb you might think it is, asking those questions and getting answers, even if you have to get the same answer 4 times until it finally kind of is phrased in a way that makes sense and clicks, really do that. Be sure you do that. Okay, I've spent a lot of time talking about that, but the biggest thing I want to make sure anybody going through this series at home by themselves is sort of has that proper context of everybody can do it. It's really just a matter of how long you have to do it, how long you have to struggle with it until it kind of clicks together and it kind of makes sense, and then it all kind of will go on. We'll move on smoothly from there. Okay. All right, so let's apply the mesh current technique. So because I talked for way too long there, I was given this strange, depressing pep talk there for. So process, identify your meshes, identify them, essential meshes, label them, and then we're going to do a Kirchhoff's voltage law. So unlike in node voltage, we had this extra step of we got to label stuff and then we got to call one of them 0 volts. We don't get that with mesh current. We don't get to just take a mesh in our circuit and say this is 0 amps, unfortunately. So we kind of have to write an equation for every mesh, but in a way it simplifies the process a little. And then once we do the KVL equation around each mesh, we're going to solve the system of equations to find the mesh currents, and then recognize that the unknown currents that were shared between two meshes is going to be the combination of those mesh currents, and then solve for whatever unknowns we have to solve for. Okay, let's actually do an example here. Okay, so we have pre-labeled for you this example here. So we have pre-labeled, we have 2 essential meshes here, or 2 meshes, I should say. And we're going to go around each one of these now and write the Kirchhoff's voltage law. So starting here, we're going to make our way around this mesh, writing the Kirchhoff's voltage law equation. So I'm going in the low potential side of this supply and coming out the top. And again, I'm going to write voltage drops to be consistent. So I'm coming in the low side, coming out the high side. That's an increase of 100 volts, which is a voltage drop of negative 100. Getting to this 4 ohm resistor, my current IA is flowing in this direction. So the voltage drop is going to be V equals IR, which is going to be IA times 4. Now, one of the biggest things students struggle with, and I'm just going to stop here really quick, is when I do this really quickly. When I just say, oh, okay, my voltage drop across this resistor in this direction is going to be this current IA times 4. And a lot of students, that's where they're like, wait, how did you know what direction it was going to be? So in this case, and one thing to keep in mind, when I'm doing this work in this video series, I hate using the equation V equals negative IR. I hate the equation V equals negative IR. I try as much as I can not to use the expression V equals negative IR. And we have to use V equals negative IR whenever we have a situation where we have labeled current entering the labeled negative terminal of something. And so sometimes what I'm doing is simultaneously I'm sort of picking a current in a direction to correspond to a voltage in a direction that I want, such that I can still use the equation V equals IR. And in this case, I'm looking for the voltage drop, and I'm going to use the current in this direction, which means I use the V equals IR version. This is not just coincidence. There's a reason I chose clockwise loops for both my currents and for both the direction in which I write my voltage drops. Because when I have labeled currents clockwise, and I travel around these meshes clockwise in order to write my voltage drops, then typically the current entering the positive terminal for the drop is going to be the current that's in the direction I'm going. So it's and I'm not sure I made anything better by just talking about this for a minute, but whether or not, the whole knowing which version of the voltage it is, knowing which version of the equation it is, knowing what direction it's going to be, sometimes I skip through it kind of fast, but we can always kind of stop. I'll try to somewhere along the line, stop and we'll talk about this a little bit more. Sometimes I try to sort of anticipate what might be confusing people and talk about it. It might be boring to some people. It might be interesting to others, but I do know this is something people struggle with. And you should note that the reason I typically use the equation V equals IR, and the reason I typically have currents entering a positive terminal in whatever positive direction is unique, is because I'm sort of trying to, when I get to choose my process, I'd rather have a process that lets me use the equation V equals IR. Okay, long enough. So we did the voltage drop across the supply. We did the voltage drop across the 4 ohm resistor. Now we're going to get to the voltage drop. So the voltage drop is going to be oriented like this across this 10 ohm. And this is where we have an interesting situation here, because there's 2 currents here that we're dealing with. We have mesh current IA, which is flowing down like that, and mesh current IB, which is flowing up like that. Well, like I just said, if I'm looking for the voltage oriented like this, and I'd like to use the equation V equals IR, then I want an expression for the current flowing down in this direction. And the current flowing down in this direction, IA was flowing down in this direction, and IB was flowing the other way. So IB is labeled flowing up, and IA is labeled flowing down, and I want the expression for the current flowing down. So I'm going to, and again, I want the expression for the current flowing down so that I can use the equation V equals IR here. So I'm going to use, for the total current flowing down, IA minus IB. So my total current flowing down is IA minus IB, and multiply that by 10 to get the voltage drop. And all of that equals 0. So another way to think about this is, what's my current flowing down? Well, I have IA amps flowing down here, and I have IA flowing down here, and I have negative IB flowing down here. So one way to think about it is, the currents flowing in the downward direction are IA and negative IB. And so it's the sum of those two that give me the total current flowing down. There's, you kind of just have to think about it several different ways until there's one that you prefer to think about. I like to think about it as IA is the current flowing down, IB is the current flowing up, and I want the current flowing down so I can use V equals IR. And yeah, so that's the way it is. Okay, so well, we got one equation. And sometimes with these, just doing it multiple times is the best way to deal with it. All right, so we got one of our equations. Let's now do the equation around loop IB. So for loop IB, we're going to be going around here. Now immediately, we're going to be getting to this 10 ohm resistor. And look carefully at what I'm doing here. I want the voltage drop across this 10 ohm resistor. Going in this clockwise loop, I want the voltage drop. The voltage drop is oriented in this direction, positive here, negative here. That is the voltage drop in the direction I'm traveling around this loop. You'll notice that's the opposite direction of the voltage drop for the previous version I did, because for the previous version, my loop was coming down at the time that it got to that point. And in this version, my loop is going up at the time I get to this point. So you might immediately recognize, well, this voltage here is probably going to be negative of the previous one, and that's true, but I can think about it a different way. I can think about it as, I want to find this voltage as labeled, and if I want to use V equals IR, I need to have the current flowing into this positive terminal. So what is the current flowing into this positive terminal? Well, IB flows into this positive terminal. IB is flowing in that direction. And IA is flowing the other way. So the current flowing into this positive terminal oriented like this is going to be IB minus IA. And that's all multiplied by 10 to get the voltage drop. So you'll see these two equations here are the opposite of each other. Oops. These two equations are the opposite. This one, to take this equation and multiply it by -1. You multiply by -1, you get negative IA plus IB. Negative IA plus IB, right? So we got essentially this negative equation, which you'd expect, because in one case we were writing the voltage drop top to bottom, the other case we were writing the voltage drop bottom to top. But we got it by thinking about this two different ways. And the way that I think about it in my head is, I desperately want to use V equals IR. So I always personally want to represent currents as the currents flowing into the negative to the positive terminal. If I have a choice of currents and I can choose the current as represented flowing into the positive terminal, then I can just use V equals IR. So that's typically what I do. But that's what I'm doing when I do this, is I am picking a way to represent my current such that the current I'm representing is entering the positive terminal so that I can use V equals IR. Okay. All right, so now we're going to keep going around this loop. We're going to go the voltage drop across the 5 ohm. Well, that's going to be this current, which is IB, times the voltage, which is 5 ohms. And then lastly, the voltage drop as we move down here, that's labeled, that's just 40 volts. Okay, 2 equations, 2 unknowns. So now it's just a matter of math. Now we've gotten these currents. Now it's just a matter of math. So let's do the math. So on this top equation, I have 4 plus 10, so I have 14 IA. And then I have negative 10 IB. And I had 100 on this side, but I flop it over to the other side of the equation, that equals 100. Now let's do the second equation. Let's clean that up. How many IAs do I have? I have negative 10 IA. And then I have 10 IB plus 5 IB is 15 IB. And we got a 40, flopping it over to the other side of the equation. We got a negative 40. Okay, now you know me. You know how I like to get rid of my variables. So I'm going to multiply this equation both sides by a 3, and this equation both sides by a 2. And when I do that, I get 42 IA plus negative 30 IB equals 300. I kind of messed this up. Didn't leave myself enough space here. And then this equation multiplied by a 2, I get negative 20 IA plus 30 IB equals negative 80. And then you know me, I add these things together. So when I add these together, I get 42 IA and negative 20 IA. That's going to be 22 IA, and that equals 300 plus negative 80, that's going to be 220. Well, this is feeling good. We get IA equals 10. And plugging that in wherever it's convenient. We'll plug it into here. So plugging in IA equals 10, we have negative 100 plus 15 IB equals negative 40. So IB equals let's see, IB equals negative 40 plus 100, which is 60. Divided by 15, which is 4. Okay, perfect. Sorry, I froze a little bit thinking there. That happens. Okay, so IB equals 4, IA equals 10. So that means that, just to go back here, that means that I had, swirling around in this circle, I had 4 amps. And swirling around in this circle, I had 10 amps. And which means that, you know, there's 10 amps through here, there's 10 amps through here, there's 4 amps through here, there's 4 amps through here, but where these intersect, I have 10 imaginary amps flowing down, and I have 4 imaginary amps flowing up. So what's my actual current in this branch? So I3 in this case is going to be IA minus IB 10 minus 4 6 amps. So in actuality here, I have 6 amps. So can I think of 6 amps as 10 amps swirling down, 4 amps swirling up? Okay, you know, that's fine. Just, you know, same thing. As long, you know, the fact that there's not actually these two counterflowing currents, like it's like two rivers colliding or something, the fact that there's not actually those two there, the math works out the same either way. As long as we remember that when we have a circuit element, or we have a branch in our circuit that is the intersection of two of these meshes, the current at that intersection is the combination of those two mesh currents. So that's the biggest thing to remember. Okay. Repetition. Right? Repetition is what gets us. So let's do another mesh current example, and then after we do this example, we'll call it good for this lecture video. Take a break, but we only do one example. It's easy to forget, so let's do another one. And let's do one that's so complex that we have to start working in linear algebra here. Because some of you probably in the last video, whenever you see me write equations, you've probably all been begging for me to like plug a matrix in somewhere. Because a lot of you probably are much more comfortable with a matrix than sort of freehand solving equations. I am with you. I am also much more comfortable with a matrix solving equations. But to be intellectually honest, I do it the hard way as well. just so you know. And the other thing, to be intellectually honest, the whole reason we're doing these techniques is to make them easy enough that you can solve them by hand, basically. So to a certain extent, if you're going to switch to a matrix, technically you can just make 6 equations, 6 unknowns, and you could just do it the long way. So partially I do it by hand also just because the whole point of this is to simplify to the point that we can do it by hand to a certain extent. Okay, let's do this circuit here. So doing this circuit, we're going to label our essential meshes. I'll call this, we'll call this one I1. Call this one I2. So I always do clockwise meshes like this. And what's the benefit of clockwise meshes? Let's go back to the previous slide. You'll notice in this equation I had IA minus. IA minus. And in this one I had IB minus. IB minus, So when you do clockwise meshes, what you see show up is you will see that whatever loop you're doing your equation around, whatever mesh you're currently doing the KVL equation around, if you're consistent about clockwise loops and doing voltage drops, it will always be that mesh current minus the other one, that mesh current minus the other one, that mesh current minus the other one. So there is value in consistency in that you start to see this pattern show up with the equations. Okay. Let's do, man, these pollens and stuff are killing me. I'm burning through like a set of contacts every 3 days. It's brutal. So even in my shed here, I am in a shed, by the way. But one benefit is my shed has an air handling unit. So I have an air filter for when I'm welding in here. So I'm gonna turn that on for a sec. Oh God, I hope that's not too loud for the video. But the pollen in here is just getting me. So I'm gonna suck it through a HEPA filter. Okay. So let's do this one. So let's do going around mesh I1. We're going to have, so around mesh I1. So starting here, I always start bottom left corner. Not sure why. It doesn't have to be that way. We go up 40 volts. That's a voltage drop of negative 40. Now we go going left to right across that 2 ohm. It's going to be I1 times 2. Now going down through this 8 ohm, now we have this situation, I'm looking for the voltage drop across this 8 ohm. If I want to use V equals IR, I have to have the current flowing into the positive terminal. The current flowing into the positive terminal is I1 minus I2. So this current flowing down, I1 is flowing down, but I2 is flowing up. So the total current flowing down is I1 minus I2. And that's multiplied by 8, and that'll equal 0. One equation down. Second equation for I2. Not equals, leave a colon here. All right, starting down here, we're going around. Now we want the voltage drop in this direction. So if I want the voltage drop in that direction, I need the current entering the positive terminal in that direction, which in this case, what's that current? Well, I have I2 is entering the positive terminal, but I1 is exiting the positive terminal. So the current in the direction I'm looking for is I2 minus I1. And again, when we're analyzing I1, it's going to be I1 minus, etc. When we're analyzing I2, it's going to be I2 minus, etc. If we're consistent about clockwise loops. Okay, 6 ohm. That's going to be I2 times 6. And then here, if I want, as I continue going around this loop, if I want the voltage drop in this direction and I want to use V equals IR, I have to use the current in this direction. That's going to be I2 minus I3. Well, that equals 0. Okay. Now, I3, last one. So now let's go around mesh I3. Starting here, in this case now I want the voltage drop from here to here. The voltage drop from here to here using V equals IR is the current entering that positive terminal. Well, I3 is entering the positive terminal, but now I2 is the other way. So it's going to be I3 minus I2. And when I say I2 is the other way, I mean I2 is now, because I'm looking for the voltage drop in the opposite orientation now I2 is entering the negative terminal instead of the positive. So now we're flipping it, right? Times 6. But again, when we go around I3, it's I3 minus. When we run around I2, I2 minus, I2 minus, I2 minus. Consistency helps prevent errors here. And then the 4 is going to be I3 times 4. And then plus 20 equals 0. Let's clean these up a little bit. So let's clean these equations up. So let's go to the first equation here. How many I1s do I have? I have 2 plus 8. I have 10 I1s. And I have negative 8 I2s. And all that, we had a 40 on the left side. Let's flop it over so we get a 40. Second equation, how many I1s do I have? I have negative 8 I1s. How many I2s? 8 plus 6 plus 6, so that's 20. How many I3s? We got negative 6 I3. And that equals 0. And then last equation, how many I1s? We got no I1s. How many I2s? Negative 6 I2. How many I3s? We got 6 and a 4. That's a 10 I3s. And all that equals negative 20. Okay, now I'm leading us to somewhere here. I'm leading us towards a matrix approach to solving this. So that's what I've done here. So I've kind of written these equations with sort of coefficients for these different variables here, with my constants off on the other side of the expression. I'm setting the ball on the t-ball stand so I can knock this thing out of the park, right? That's what we do. Right? Okay. All right. So I'm going to have to probably switch back and forth, but let's look at these equations here. So refresher on linear algebra. Let's stop where we are, put a pin in this. We have our set of equations. I don't want to solve these by hand. You might want to solve, you might think it's easy to solve by hand. Maybe it is easy for you, but these equations, I'm probably 30% chance of making a mistake. I guess 30%. If I had 4 equations by hand without using linear algebra, probably 50, 60% chance of making a mistake. 5 equations, good night. It's not going to happen. There's going to be a mistake somewhere. I'm going to miss a positive or negative, or I'm going to flub a number for, I don't know. Okay, so refresher on linear algebra. Anytime we have the expression, let's say we're solving for x, and we have this expression ax equals b. How do we solve for x? Well, divide by both sides by a, and you solve for this. Or another way to put that is take the inverse of a and multiply both sides by the inverse of a, which is what we're doing here. And then that leaves us with this expression for our unknown variable x. X is equal to the inverse of a times b. So switching our equations to this sort of linear algebra approach, going back to this, what if we had I1, I2, and I3, and that's our x. And now we represent our equations as coefficients in a matrix. So the first equation, I had 10 I1, and then I had negative 8 I2, and then how many I3 did I have? 0. Oops. Equation 2, I had negative 8 I1, 20 I2, and negative 6 I3. And the last equation, I had 0 I1, negative 6 I2, and 10 I3. Okay, looks about right. And then equals. What do these equal? 40, a 0, and a 20. So if I'm trying to solve for these unknowns, right, and that's what I am doing, the whole point of mesh current is to solve for these unknown mesh currents, then I want to, in order to get my equation in this form, I'm going to have I1, I2, I3 equals 10, negative 8, 0, negative 8, 20, negative 6, 0, negative 6, 10 times 40, 0, 20. So what I do is in my calculator, I create this matrix. I take the inverse of it, and then I multiply it by this matrix. And then that will give me brackets here. So my calculator, your calculator is probably better than mine. I got one of these HPs. Yeah. Come on, window. There we go. You can see my little green screen back there. Okay, I got one of these HPs. I'm going to do it. There's no cheating here. If I make a mistake, you all get to see it. So I'm going to enter my matrix. You might want to skip this, though, if you don't want to see it. And okay, so on my calculator, can't get this. I get my butt. Oh no, it's not going to happen. It's not going to happen. It's too good. Too good at finding my. Can you see that? I don't know if you can see that. Anyway, that's my matrix. And then I take the inverse of that. And now I multiply it by a second matrix, which is going to be 40, 0. Oh, wait a sec. Negative 20. Sorry. Ooh, that was quick. That was close here. Negative 20, negative 20. Almost. Not today. I caught that one. Got that one before it became an issue. Okay. So this matrices are where HPs get a little bit weird, but that's what it looks like on my calculator. The inverse of the first one and the second one, multiply them, and this is my answer. Oh, this is bad. Hopefully you can see that. I don't know. Anyway. Okay. It's reversing it. Anyway, 5.6. I got 5.6, 2, and negative 0.8. Okay. Now, if you're like me, you don't trust yourself. I don't trust myself pretty much ever. So, especially when I take a bunch of numbers and slap them in a table and go toot, 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 and have a calculator spit out the answer, my faith in this whole process working is always very low. And here's the thing. If I'm taking a test, there's not much I can do. Like, if I'm taking a test, I don't have time to triple, quadruple check my work. Although in this class, typically the final, there's not really a time crunch on the final. So if you do feel crunched in tests in this class, the final is usually your saving grace to kind of prove how well you can do stuff when you aren't under a time crunch. But I don't trust myself. So what if I don't trust myself here? How can I check my work here? How can I make sure that this might be correct? Well, let's go back. So we got 5.6, 2, and 0.8 here. So 5.6, and then we had 2, and then negative 0.8 here. So let's just verify maybe that these currents are right using Kirchhoff's voltage law. Let's just go around loop I1. Let's just go around loop I1. No, let's go around loop I2 for fun. Let's go around loop I2. So loop I2, so the sum of these voltage drops should equal 0. So we already have the equation written here. So we could just plug the numbers in, but let's think about it. I'm going to think about it a little more. Kind of want to write this down as I do it. So I like I2 because it's going to touch all of my currents in my equation. It doesn't guarantee it's right, but at least at one sanity check here. So going around this, adding up these voltage drops here. So that voltage drop across that 8 ohm resistor is going to be I just deleted my currents, didn't I? Yeah. So it's going to be I2 2 minus I1, that's going to be 2 minus, so it's going to be 2 minus 5.6 times 8. That's going to equal 28.8. Nobody can see that. Okay, now the voltage drop across the 6 ohm, that's easy. That's just going to be 2 amps times 6 ohms. Gotta be able to do that one in our head. So now we've gone down 28.8, down another 12. So we'd better go down a negative something here. All right, let's see. Oh, I'm sorry. This is negative 28.8. Sorry. 2 minus 5.6. Negative 28.8. Negative 28.8. Okay. So we went down negative 28.8, then down 12. So what's left here? 6 ohms. So it's going to be I2 minus I3. It's going to be 2 minus 0.8 times 6. Sorry, 2 minus negative 0.8. Whew. Times 6. 16.8. So negative 28.8 plus 12 plus 16.8, does that equal 0? It does. So that was one way that we could check. We could check our work by going around one of these loops, going back to these equations, plugging in those values, making sure they actually equal 0. It's a good sanity check to check your work. My technique, if I'm doing a test or a quiz, I'll go through it once, assume my math was right, but then, leave a star for myself or something, and then go back and double check. I'll usually, follow up, go back, double check afterwards. Okay, so we've now done 2 examples of mesh current. For the second one, we had 3 equations, and I showed you how to do the linear algebra matrix approach. So in the next video, we are going to, just like we did with the node voltage where we had special cases, in the next video, we're going to look at some of these special cases that show up sometimes when we